Today, I'm going to be talking about clustering under perturbation stability in near linear time. And this is joint work with Pankaj Agarwal, Xianqi Cheng, Kamesh Munagala, and Emma Wells. So we're talking about a clustering problem, and specifically clustering a set of points in Euclidean space where we're given the number of clusters we want to find, k. And we'll want to find a set of k centers and then assign each point of x to its closest center. And there'll be associated cost for a solution. So S is a set of k centers. We'll associate a cost of that solution. And we'll use some of the standard problems. So k median, where the cost of a clustering assignment is the sum of the cost of the distances. K-means, where the cost is the sum of squares, and k-center, where the cost is the maximum distance between any point and its assigned center. So here, delta is just the Euclidean distance, and this delta PS notation just means that we assign a point P to its closest center in S. So even in low-dimensional Euclidean space, these three problems are NP hard. So what you might try to do is use an approximate solution. So typically approximation algorithms give you a guarantee that the cost of the approximate solution is within some factor of the cost of the optimal solution. But there's no structural guarantee necessarily on this approximate solution. So the approximate solution may look very different from opt, even though their costs might be similar. So there's been a lot of work designing approximation algorithms for these classic clustering problems, but in practice, heuristics work very well. So we might be interested in how to explain this phenomenon in a theoretical framework. So the way we're going to look at this is by making an assumption on the input data. So we're going to assume that the input is stable. And what I mean by that is that if we perturb the points by a small amount or change the distances, the optimal partition or the optimal clustering does not actually change after this perturbation. So here's an example of three clusters. And you can see that even when we move the points slightly, the three optimal clusters will be the same. All right, so to formalize this notion, we say that an instance is alpha stable if the optimal partition does not change for any delta prime, where delta prime is this new distance values that's within a factor of alpha of the original distances. So we note that you don't have to change every pairwise distance by the same amount. So you can change any pairwise distances by at most a factor of alpha. So intuitively, when alpha is large, it means the instance is very stable, i.e. we can perturb or move the points a lot, and the optimal partition will remain the same. So intuitively, that would mean that opt is easier to find. And indeed, this is the case. So in previous work, authors have focused on giving polynomial time algorithms that find the optimal solution for a stable clustering problem. So there was an algorithm that works in general metric spaces when alpha is at least 2. So the stability parameter is 2. And in fixed doubling dimension, you can actually relax this assumption to alpha being at least 1 plus epsilon. And so this previous work really focuses on trying to decrease the assumption on alpha, and not so much on the runtime. So they want to give polynomial time algorithms, and they want to make the smallest assumption on alpha possible. And we note that this problem remains NP hard in general metrics when alpha is less than 2. So in contrast to this previous work, our work is focused on designing a clustering algorithm that runs in near linear time. So that could be run on large data sets. And we would still like our algorithm to give the optimal solution, right? So if the input is stable, we want to know what's the assumption we need to make on alpha so that we can design a fast and exact algorithm. So here's our first result. So again, we're in Euclidean space and d dimensions, and we fix d. And for k-means, median, and k-center, for any 2 plus root 3 stable instance, we can solve the problem using a dynamic program in near linear time. And this tilde notation is just hiding any logarithmic factors. And then we'll also talk about a result for k-median. For any 5 plus epsilon stable instance of k-median, you can actually solve this using a local search algorithm in near linear time. So we note that this second result is slightly weaker than the first, but we think the proof might be of independent interest. So we're going to start by talking about the dynamic programming algorithm. Right, so we first make a few observations, and the first is that for any 2 clusters of the optimal solution, these clusters are actually well separated. So if you look at any 2 points within a cluster A, so this distance between x and y, it's going to be smaller than any distance between clusters, so any of these ZQ distances. And additionally, in a previous work, it was noted that every cluster of the optimal solution is actually a subtree of the minimum spanning tree. So we might think that we can now do some sort of dynamic programming over this tree. And we also note that the longest edge of the minimum spanning tree can't be within one cluster of the optimal solution. And again, this comes from our well-separated property, because otherwise this would just mean that the longest edge UV would be within one cluster, and this would be longer than some distance that spans between 2 clusters. So putting all these observations together, we note that every cluster of the optimal solution has to be in the same connected component of the MST without this longest edge E. Right. So our dynamic programming algorithm, we'll start by constructing the MST for our instance, and then we'll find the longest edge of this MST. And we note that if this edge is UV, then we'll want to recurse into the subtree XU and XV. So XU is the set of all points of X that are rooted at the subtree, rooted at U, node U. So then we let mu YL denote the optimal L clustering of a set of points Y. And so the quantity we're interested in is just mu XK. So if k is 1, then all we need to do is find the one clustering cost of the points of X. And then otherwise, we want to recurse in each of these subtrees XU and XV. And so to do that, we need to guess the number of optimal clusters in each of the subtrees. So we look at all possible guesses, and we just take the minimum over all of these. Right. So we can compute the MST in near linear time. And then for all nodes of the MST, we want to compute the one clustering costs of all the points rooted in the subtree rooted at B. And we do this independently, and suppose that takes tau in time. Then once we have this, we can compute the k clustering cost for a set of points X in a bottom-up fashion. So there are nk entries, and each takes O of k time to compute, because we have to guess these number of optimal clusters. So in total, this will take nk squared time. So in fact, the DP runs in this near linear time. So all that we really need to show is that we can compute all the one clustering costs in near linear time. So the idea we're going to use to do this is we're going to use some sort of dynamic data structure. So we want to maintain a data structure for each node V of the MST. And we would like the data, given the data structure, we would like to know the one clustering cost of the points in that subtree in constant time. And we'd like to be able to insert a point into the data structure in constant time. Right, so using the second property, we could construct the data structure for node V by taking the data structure for its larger child W and inserting the points from XU one by one into the data structure for this larger subtree. And so if we do this, the total time it would take to compute the data structure for all nodes would be the total number of insertions we have to make. And so it can be shown that this is actually just n log n. So what we actually maintain in this data structure so that we can get this first property depends on the problem. So we're going to take a look at the case center problem. So we want to look at the data structure for the one center clustering cost. And instead of the L₂ metric, where we want to minimize the ball containing the points xv, we're going to look at the L₁ metric. So again, we want to compute all the one clustering costs where we're using the one center distance in the L₁ metric. And this is actually equivalent to finding the smallest L₁ disk containing the points xv, right? And then the one center clustering cost will just be half of the larger diagonal distance. So half of the larger, so this will be the radius of the disk. So in this example, we see in these four directions, these are the four extreme points. And so the one clustering cost for k-center here will just be half of this red distance. Right, so in 2 dimensions for the L₁ metric, all this data structure needs to contain is these four extreme points in each of these four directions. And so now we can see that given this data structure, it's very easy to find the cost of the one center clustering, right? This can be done in constant time. And to insert a new point, we just need to check if this point is extreme in any of these four directions. And this can also be done in constant time. Right, so now that we have this data structure, that means that we can compute all these one center clustering costs in the L₁ metric and near linear time. But again, we're in sort of a simpler case of the L₁ metric instead of the L₂ metric. But the idea is that this isn't too far off. So we can actually use the polyhedral metric as an approximation to the L₂ metric, where the ball in the polyhedral metric is just this regular convex polyhedron. So, and then we'll say that a distance function is a beta approximation of the original distance if all the pairwise distances are within a factor of beta of the original distances. So the intuition is that if we have an approximation of the L₂ metric, then the optimal clustering solution doesn't change after we change this metric. And in fact, in the new metric, the instance remains stable. Right, and so as we increase the number of sides on this regular polygon, the approximation to the L₂ metric improves, so beta decreases. So if we take enough sides, then our approximation will be tight enough that we can use the polyhedral metric instead of the L₂ metric. And in fact, this is nice because in the polyhedral metric, we can solve these one center clustering problems using similar ideas from the L₁ metric we just saw. So to summarize, we want to compute all of the one clustering costs for each node of the MST. And so for k-center, we'll switch the polyhedral metric, and then the data structure will just have a fixed number of directions. We need to keep the extreme point in each direction. And given these points, we can easily compute the one center clustering cost. For k-means, we actually can directly compute the one mean efficiently in the L₂ metric. And for k-median, we'll also switch to the polyhedral metric, but the actual details of the data structure are a little bit more involved. So we leave the details to the paper. So we use stability in a couple places for this algorithm. We use it so that we could switch the polyhedral metric, and this would not change the optimal clustering. And the switching of metrics allows us to compute these clustering costs efficiently so that we get a near linear time algorithm. And then we have to have this stability assumption so that we can actually run this dynamic programming algorithm and it will be correct so that the optimal clustering respects the minimum spanning tree. And as we noted in our results slides, we also have a local search algorithm that works for k-median. So I'll take the rest of my time to talk about this algorithm. Right, so recall that the k-median clustering cost is just the sum of distances for each point to its closest center. So local search is obviously a pretty simple algorithm. We start with k arbitrary centers as our solution. And we're going to keep locally editing our solution until the cost stops decreasing. So we'll compute the best one swap, i.e. the best point of our solution to drop and new center to add so that our clustering cost decreases the most. And we'll make this one swap, and we'll keep repeating this step until the clustering cost stops decreasing. And then we'll return this as our solution. Right, so if this is our current solution where these darker points are our three centers, then the best one swap might be dropping this point x from our solution and adding this point y to our solution. And we can see that if we did this and these were three new centers, then our clustering cost would decrease. And in fact, for our 5 plus epsilon stable instance, even just this one swap local search algorithm is optimal. So we note that there's actually a similar algorithm given with a smaller assumption on alpha, but this algorithm uses a large swap size. So in order to run our algorithm in near linear time, we need to make this proof work for the one swap case. So we want to analyze the cost of our solution S against the cost of the optimal solution. So the idea is to do this point by point. So to see how each point is contributing to the cost of the solution S. So for each point, we associate two centers, where n in star p is the closest center of opt. So this is where p is assigned to the optimal solution. And then n and p is the closest center in our current solution. And so with these two centers, we can classify each point into 4 subsets. So for example, in x11, p is assigned to its optimal center, and this optimal center is in S, right? So we know that the cost of p contributing to our current solution S is the same as the cost of p in the optimal solution. Whereas in x10, p is currently assigned to some optimal center, but the center it's assigned to in the optimal solution has not been added to S yet. So we know that the cost of p in our current solution is actually more than the cost of p in the optimal solution. And similarly in x01, the center p is assigned to in the optimal solution has been added to S, but p is currently assigned to a point in S instead, which means this point in S is closer than its optimal center. But sort of in each of these 3 cases, p is somehow associated with a center of the optimal solution that is in S. Whereas points in x00, p is assigned to some point in S, and the center p is assigned to in the optimal solution has not been added yet. So in some sense, 3 of these cases are sort of easier to bound the cost of P because it's associated with some optimal center that's an S. But the x00 case is hard because P is split, so we don't really know how to bound the cost of P. So instead, what we do is we bound the cost of our current solution by the cost of opt and the cost of the subset x00 in the optimal solution. So we say that a clustering is C good if the current clustering cost is at most opt, the optimal solution cost, plus C times the cost of x00 in the optimal solution. And in fact, if X is C+1 stable, then any C good clustering is actually optimal. And as long as our current solution is not 4 plus epsilon good, then the best one swap actually decreases the cost of our current solution. And it does this by a certain factor. So this will allow us to bound the number of iterations as something like order k iterations. Right, so putting these two limits together, we can see that if our instance is 5 plus epsilon stable, then the one swap local search algorithm is optimal. And in fact, we can bound the number of iterations. So we won't go into details on how to prove either of these lemmas because they're quite involved. And we won't talk too much about the running time and how to make this one swap local search algorithm run in near linear time. So we'll just give a brief summary. So we'll pre-process data and build some sort of data structure in near linear time. And then in each iteration, we need to choose the best one swap, and there are nk possibilities. And so we need to find the cost of each one swap so that we can choose the swap that decreases the cost the most. And in fact, we can do this in order k to the 2d minus 2 time. And this will involve, again, a change of metric to polyhedral metric so that we can query this data structure and find the cost of a clustering quickly. And we saw that we could bound the number of iterations using the previous lemma. And so putting all of this together, for a 5 plus epsilon stable instance, the optimal solution can be computed in times k to the 2d time. And so we leave most of the details to the paper. So again, stability allowed us to do a couple things in this algorithm. First, it told us that local search actually finds the optimal clustering and that the number of iterations it takes is small. And we know that we can use the polyhedral metric to approximate the L₂ metric, and this will not affect the optimal clustering. And in the polyhedral metric, we're able to design more efficient algorithms to compute the cost of a clustering. So just to talk briefly about future work, I think the most obvious future work is to try to decrease the assumption we need on alpha. So right now our assumption on alpha is quite large. But again, we would like to design near linear time algorithms for instances that are less stable. So one direction would be to verify the tightness of our algorithms. Perhaps they work for a smaller value of alpha. Or for the local search algorithm, if you allow a larger swap size, you can actually decrease this assumption on alpha. But even if you move from one swap to two swap, now you have a quadratic number of swaps and you can't possibly try all swaps to find the best one. So you sort of need a new idea there. All right, that's all I have. Thank you.